Hello, this is Brian Washburn again. I'd like to give an introduction to Hamiltonian mechanics. Um, so, when we talked about conservation principles, we looked at under when the Lagrangian was not an explicit function of time, the total mechanical energy is conserved for a system. Okay, and that's an important result. The other thing we showed was that if the Lagrangian is cyclic in a variable, the generalized momentum associated with that variable is conserved. So those are very important things for solving problems. However, even though Lagrangian mechanics provides a nice formalism to look at conserved quantities, you still kind of have to dig into the equations a little bit to get those conserved quantities. For example, the mechanical energy just doesn't pop out. And even the generalized momentum, if it's conserved, you have to work a little bit to get to it. So wouldn't it be nicer to have a form of mechanics where these conserved quantities just kind of pop out, like the mechanical energy and any type of conserved momenta? And that's what kind of Hamiltonian mechanics does for you. These conserved quantities kind of come out. And so let's look back at this definition of what I call the Hamiltonian. And notice the Hamiltonian, okay, so here I wrote it a little differently. The Hamiltonian is a function of three things: the generalized coordinate, the generalized momentum, and time. And it may be explicitly a function of time. Now, if that's the case, it's not conservative, but I can always define a Hamiltonian for a non-conservative system. Now, how do I get the Hamiltonian? Well, what I have to first do is get the Lagrangian. So I get this thing here. And the Lagrangian, in general, may be a function of generalized coordinate, generalized velocity, and time explicitly. And then I have to put it into this equation here. Now, this equation here is basically a linear transform, or in some fields, it's called a Legendre transform, or transformation. And basically what it does is it converts a function L, which is a function of q dot in time, to a new function h, which is a function of q, p in time. All right. Now, only time this is going to be conservative, the Hamiltonian is going to be conservative. We'll talk about when it'll be conservative, but the gist of that story is that the Lagrangian cannot be an explicit function of time. Okay, that's one, and we'll talk about different. So this Hamiltonian can be the total energy for a specific case. All right. Now, since we rewrote our Lagrangian in the form of a new function with new variables, okay. So remember, Lagrangian is a function of, in general, q and q dot. Okay, that's my Lagrangian. We've now rewritten everything in terms of two different variables instead of q and p sub q. Okay, where q and p have a nice name, they're called canonical variables. Canonical variables. That's what they're called. Okay. So now let's see if we can get new equations of motion from this new expression of the Hamiltonian. So instead of using the Euler-Lagrange equation, we're going to get a new set of equations. Okay. So let's look at those, and they're called the Hamilton equations of motion. So how can we get these equations of motion, the Hamiltonian equation of motions? Well, what we can do is we can remember my Hamiltonian is a function of. So remember my Hamiltonian h is a function of, in general, q and p sub q. So what we can do is just start taking derivatives, partial derivatives of the Hamiltonian with respect to q and p sub q. So if I take a look at the derivative of Hamiltonian respects to q, okay, so then what happens there is that now what I'm going to do is, so what is again, just to remind you what the Hamiltonian looks like. The Hamiltonian looks like this. All right, so if I take the derivative of that with respect to q, okay, now the thing you got to remember is that q dot may be a function of q and p, okay. So then when I take the derivative of, and then p is just p, so then when I take the derivative of the first term, and let me write that term here, hold on. So what I'm going to do is I'm going to take the partial of h respect to q. Now this is, I rewrote h here for you. Now p is just p. However, you got to be careful about q dot. Remember, we're doing kind of a transformation from q to q dot to p and q. So when we do this, we have to, q may be a function, q dot may be a function of q, p sub q, and time explicitly, depending on what we're doing. So then when I take the partial of h respect to q, well then p is not going to be a function of q. P is this p, but q dot may be a function of q. So I take the partial of q dot respect to q. All right. Then I have the partial of L respect to Q. Well, L is a function of P of Q. Okay. And then, however, L is also a function of Q dot. Okay. So then I have to take partial L respect to Q dot and partial Q dot respect to Q, again using chain rule. So then this whole term here is really the result of, and there's a, I forgot there should be a minus sign there. But this is a result of the chain rule of taking the partial L respect to Q, because Q dot may be a function of Q. Now, if you take a look at this first term, well, okay, that's P times Q dot, the derivative of Q dot respect to Q. This is partial L respect to Q. And then this guy here is partial L respect to Q dot. Well, that is P, okay. And so then what I get from that is I get this term here, which is equal to the same thing here minus. So those terms cancel out. So then in the end, I get minus L respect to Q dot. Okay. Now I don't want L there. I want to get rid of that. And so I can use the Euler-Lagrange equation. Partial L respect to Q is equal to d dt of partial L respect to Q dot. But again, I don't want any Q dots. I want P's. That is P. And so d dt of P is P dot. So that gives me a really nice looking equation that partial H respects to Q is equal to minus P dot. Minus sign comes from that guy right there. Okay, that's a really cool looking equation. All right, very simple. Now, H is a function of Q, or a function of P. So let's take partial derivative of H respect to P. That'll be simpler. Again, looking at what I had before here. Okay. Now what I'm going to do is, so this term here, P is just P. However, so then when I take the derivative of this, that P goes away. That leaves me Q dot. But then I get P, and then I have to do the partial. I have to use the chain rule. Remember, Q dot may be a function of P and Q. So that's going to give me P times the partial of Q dot with respect to P. Okay. So this term here is the chain rule of this term here. Okay. And I apologize for that. Okay, yeah, we can see it there. And then I have to do I have to do then the chain rule of that thing right there. Okay. So then I have to do partial L with respect to Q dot. Okay. Because L is a function of Q dot, but Q dot is a function of P as well. Remember, so I'm taking partial L with respect to P, but L is I have to take the partial L with respect to Q dot with respect to P. In the end, what happens is this term here and this term cancels. Okay, remember, partial L with respect to Q dot is P. All right, and then this term and this term are the same. And so then I get a very simple expression that partial H with respect to P is equal to Q dot. So to summarize, what I have is I have now a new form of mechanics. And what I can say is I can define the Hamiltonian. Hamiltonian is a linear transformation from a function, the Lagrangian here. I stick it into this equation here. I get now a new function H, which is a function of P's and Q's in time. And then I can get the equations of motion by directly, directly by taking partial H with respect to Q minus P dot. Partial H with respect to P is Q dot. Those are my equations of motion. So the equations of motion look pretty simple. And you may say, well, that's a lot easier than use the Euler-Lagrange equation. Yeah, it is. However, when doing this, I still have to get the Lagrangian. So I have to do every problem in Hamiltonian mechanics have to do just as well, half as much work in Lagrangian mechanics as in Hamiltonian mechanics. Okay, so let's take a look at the steps. Oh, actually, let's first take a look at the steps for solving a problem. Before that, let's take a look at cyclic variables. Now, the reason why people would use Hamiltonian mechanics over Lagrangian mechanics is because of conserved quantities. And the two conserved quantities we're interested in, some conserve momentum and some conserve energy. So let's look at the how conservation of momentum shows up in Hamiltonian mechanics. Now, in Lagrangian mechanics, we define a variable cyclic. So say the Lagrangian L is cyclic in Q. That means that L is not an explicit function of Q. Okay. However, that also means that L is a function of Q dot. Now, from all that, what we say is that, well, the P sub Q is a conserved quantity. Okay, it's constant. But the thing about it is that even though the Lagrangian is not an explicit variable of Q, it always will be an explicit variable of Q dot. Okay, so even though it makes life easier, it doesn't reduce the degrees of freedom because Q dot is still there. So and it goes back to this idea that, it's momentum is conserved, not velocity. But what about the Hamiltonian? Well, if the Hamiltonian is not a function of Q, that means it is a function of P sub Q. However, P sub Q is a constant. Okay? So now, really, by instead of writing things in terms of Q dot, instead of I write in terms of P, I have actually reduced a degree of freedom. So a problem say I have a two-dimensional problem in Lagrangian mechanics, it will be and say angular momentum is conserved, it'll be a one-dimensional problem in Hamiltonian mechanics. And that's the advantage, is since my variables are explicitly Q's and P's are constant, and so then then I lose a variable or I lose a degree of freedom. So that's the advantage of using a Hamiltonian formalism. Okay. What's the disadvantage? Let's take a look. Now, before I talk about disadvantages, let me first talk about, Hamiltonian. We talk about the Hamiltonian in context of energy conservation. Is the Hamiltonian equal to the total mechanical energy? In general, no, it's not. It is not equal to the total mechanical energy. Okay. It is only equal to the total mechanical energy under two conditions, or really one condition, is that the Hamiltonian is not an explicit function of time. In general, since the Hamiltonian depends on the Lagrangian, if the Lagrangian explicit function of time, the Hamiltonian will be an explicit function of time. So in general, the Hamiltonian will be a function of Q, P, and time. However, if the Hamiltonian is not an explicit function of time, that means that partial h respect to t is equal to 0. There's no t explicitly in the Hamiltonian. In that case, the Hamiltonian will be constant. Okay, so we can summarize that. Under what condition does that occur? Well, first of all, we have to have a conservative potential. So that means that u is only going to be a function of the q sub j's. Okay. Now the q sub j's will be a function of time, but the u will not be an explicit function of time. It will be only an explicit function of the q sub j's. The other condition we need is that, remember, I have these equations constrained. If the equations constrained do not explicitly depend on time, then I will also have energy conservation. You may say, well, when does it occur? Well, say I take a moving coordinate system, or the problem we had of a pendulum that's attached to a base that's accelerating. And in those conditions, the equations do depend on time, and it actually needs energy from the outside world to keep that moving. So that's the case. So when is the Hamiltonian equal? When is the Hamiltonian equal to the total mechanical energy? Well, when the potential energy is only a function of the generalized coordinates, and the equations constraint do not depend on time. Okay, So how do you do problems in Hamiltonian mechanics? You notice the equations of motion are quite simple. However, the method to get to those equations is more cumbersome. So in my opinion, it's a lot easier just to do things in Lagrangian mechanics. But this is the method. So the first thing you need to do is you need to find the Lagrangian. Okay, you have to find the Lagrangian. So you have to look at the system, you have to do everything you need to do for Lagrangian mechanics up to the point of getting the Lagrangian. So equations of constraint, degrees of freedom, kinetic energy, potential energy, write the Lagrangian. The next step to do is you find the generalized momentum, because the Hamiltonian is written in terms of not q dots, but p sub q's. Then what you do is you find the Hamiltonian using that linear transformation. Okay. However, when you do that, you have to make sure that you write the Hamiltonian. There should be no q dots in there. The Hamiltonian is an explicit function of only q, p sub q, and time. There's no q dots in there. And then once you have the Hamiltonian in that form, then you can just take the partial of h respect to q and the partial of h respect to p. Those give you the equations. That gives you the equations of motion. Now for each degree of freedom, you'll get two equations of motion. That's different than Lagrangian mechanics. The Lagrangian equation, you got one differential equation for each degree of freedom. Now they're equivalent, and the reason why they're equivalent is, think about it. In Lagrangian mechanics, you get, for each degree of freedom, you get one second-order differential equation. In Hamiltonian mechanics, you get, for each degree of freedom, you get one first-order differential equation, but two first-order differential equations. But as we talked before, any second-order differential equation can be written as two coupled first-order differential equations. So in the end, they're the same equations. You don't get any new physics from Hamiltonian mechanics. So let's look at an example. So what I'm going to do is I'm going to do here a simple example for a simple pendulum. Actually, no, not even simple pendulum, simple harmonic motion. And then I'm going to do a more complicated problem in another video. Okay, so here I do simple harmonic motion using Hamiltonian mechanics. First thing I do is I write down the Lagrangian. So this is a one-dimensional problem. Hopefully I don't need to really go over this. You guys should know this by now. But again, my problem is I have a spring and a mass. Oops. Let's just do it this way. So what I have is I have a spring, a mass, and a frictional surface. And it moves along the x position right there. Okay. Spring force. So the potential energy associated with that is equal to 1/2 kx squared. The kinetic energy is equal to 1/2 mx dot squared. So that's my Lagrangian, t minus u, and that's what I get. That's what I get here. Okay. So now I wrote the Lagrangian. That's pretty easy. I'm going to define a generalized momentum. And that's going to be p sub x. That's a momentum in a linear momentum in x direction. Partial L respect to x dot. That's mass times velocity. Okay, that's pretty easy. Now I'm going to write the Lagrangian. Remember, so I can write the Hamiltonian. And the Hamiltonian, let me just write it here. Let me write it there. Just give me a second. And so write the Hamiltonian there just to remind you what it looks like. Hamiltonian in this case is going to be equal to x dot px minus the Lagrangian, which is a function of x and x dot. So I do that. That's what I have here, and then I subtract that. Now notice I have x dots in there. I don't want x dots. I want p sub x's. So everywhere I have an x dot, I'm going to replace it with a p sub x. I'm going to use the generalized momentum here that I defined. So I can say that x dot is equal to p sub x divided by m. I stick that into there. Notice that here I get px squared divided by m minus 1/2. This cancels out with that one of those guys there. 1/2 p squared x, px squared divided by m plus 1/2 kx squared Then I get Hamiltonian is equal to p squared over 2m plus 1/2 kx squared. And that is the total mechanical energy. And hopefully you guys remember that, potential energy, kinetic energy is 1/2 m x dot squared. But I always can write that as, from the definition of momentum, p squared divided by 2m. Okay, so in this particular problem, the Hamiltonian is equal to the total mechanical energy. And I expected it because Lagrangian was not an explicit function of time, and the x and y's did not move with time. Okay, so that's my Hamiltonian. Now we can get the equations of motion. First thing I'm going to do is partial h respect to x. There's only this term here is an x, so the 2's cancel out. I get kx, and that's going to be equal to minus px dot. So that's my one equation of motion. Px dot equals minus kx. And that is Newton's second law. Force, the net force equals mass times acceleration. Okay. And then the second Hamiltonian equation I'm going to get is partial h with respect to p dot. P dot is in the kinetic energy term here. The 2's cancel. I get p over m x dot, and I get x dot is equal to px over m. So those are my two equations of motion. Notice what I have is I have two coupled first order differential equations. Now, I've showed you these equations before, but you may say, was this really simple harmonic motion? Well, I can show that. I'm going to take the derivative of this. That's going to give me x double dot. That's p dot divided by m. But p dot is equal to minus kx. And so what I get is I get this equation here, and that is simple harmonic motion. Okay? So wow, yeah, that was a long way to get to something simple. All right. Anyhow, we're going to see more complicated problems even. Now I'd like to talk a little bit later about why would anybody want to do this. There are very good reasons why to write problems in Hamiltonian mechanics, and we'll get to that a little bit later. But for now, we'll say goodbye.